In the previous lecture, we have started to deal with a very important problem, and that was actually the problem of helicity. Actually, in the first lecture on this helicity, we have discussed first of all what is the general meaning of helicity, and after that you have seen how the helicity of electron can be determined both theoretically and experimentally. Now today we are going to see the concept of helicity of neutrino. So this lecture will be completely based to determine the helicity of neutrino, which is an important particle emitted during the process of beta decay and the electron capture. In fact, in 1958, three scientists were able to study the polarization of the neutrino emitted in an electron capture process. So, the problem of helicity, which we will discuss today, is completely based on the concept of the electron capture process in which a neutrino is emitted. In fact, the study was regarding the K electron captured by a particular nucleus, and that nucleus was 63 EU 152. In fact, when the negative electron from the K shell is captured in the isomeric 0 minus excited state of EU 152, leading to the formation of 152 SM in an excited state of 1961 kiloelectron volt and goes to the ground state 0 plus or 0 plus. So actually in this process we will see that there will be a gamma decay, and measuring the momentum and energy of gamma photon, we will be able to measure the helicity of neutrino. So first of all, we will see how this electron capture process takes place by this particular nucleus, 63 EU 152. Actually, I have shown here that this EK half. Actually, this represents the electron of the K shell which will be captured by the nucleus EU. In fact, inside this bracket I have mentioned the state of spin. So the K electron has spin half, and this nucleus EU which captures actually this K electron in ground state has spin 0. So after capturing this K electron by the nucleus EU, we get actually the nucleus of SM152, and that is actually in its excited state. And this excited state, you can see this figure. This is actually the second excited state of this nucleus SM152. And this is actually 961 kilo electron volt above its ground state. This is its ground state, and this second excited state of SM152 is above 961 kilo electron volt. Okay. So after the electron capture, this EU nucleus is transformed into the SM nucleus, which is in its second excited state, and the angular momentum of, or you can say the spin of this SM nucleus in its second excited state is 1, and its parity is negative. This minus sign here denotes actually the parity. Okay. And in fact, the later decays by the emission of gamma ray photon of 961 kilo electron volt goes to the ground state. So you can see I have shown that if this nucleus SM152 in its second excited state suffers a gamma decay and goes to its ground state, then a photon, this gamma is the photon which will be emitted, and its energy will be what? Since energy of the excited state is 961 kilo electron volt and that of the ground state is 0, so the energy of this gamma photon will be what? This will be 961 minus 0, and that will be equal to 961 kilo electron volt. Okay, so after emitting a gamma photon of 961 kilo electron volt, this SM nucleus in its second excited state goes to the ground state. Okay, but at the same time the other transition may also take place. You can see this state 2 plus, it means the angular momentum or the spin of this SM nucleus is 2 and its parity is positive, and this is actually the first excited state of SM152 corresponding to the energy 120 kilo electron volt. So from the second excited state it is possible that this nucleus of SM may transit to the first excited state emitting a gamma photon, and this gamma photon will have energy 837 kilo electron volt. Why? Because transition takes place between the two excited states corresponding to the energy 961 kilo electron volt and 124 kilo electron volt. So the energy of gamma photon will be what? That will be simply 961 minus 124. Subtract it, you will get that this will be 837 kilo electron volt. So this gamma photon, which I am just underlining here, has an energy 837 kilo electron volt. And after that, the SM nucleus, which is in its first excited state corresponding to the energy 124 kilo electron volt, may suffer a gamma decay, and the gamma photon of energy 124 kilo electron volt will be emitted, and then it will be in its ground state. Okay, so you can say that the entire angular momentum change in this process is carried away by the emitted photon. Okay, and the capture process in this case is, you can see, this is just a transition from 0 minus state to 1 minus state. It means the initial spin of the nucleus is 0 minus. Minus actually represents the parity, and from this state the transition is in the final state where the angular momentum or spin of the nucleus is IF equal to 1 minus. And you know that if the transition takes place from 0 minus state to 1 minus state, this will be just a pure Gamow-Taylor transition. You have studied the Gamow-Taylor transition in previous lectures. So this selection rule actually permits that this transition is purely a Gamow-Taylor transition. And in this case, the spin of the emitted neutrino must be anti-parallel to the spin of 961 kilo electron volt SM52 state, as I have shown in this figure. You can see this is actually the emitted neutrino, and its spin is half, and I have shown the direction of this spin in upward direction, and this is your recoiling nucleus, which is just moving in opposite direction of this neutrino, that is, it is moving in downward direction, and its spin is also downward, and that spin is equal to 1. So you can say that actually the spin of the emitted neutrino, this nu, and the spin of the recoil nucleus. Recoil nucleus means this is Sm star, which has energy actually 961 kilo electron volt. Both have actually the spin in opposite directions. So we simply say that the emitted neutrino and the recoiling nucleus must have a spin anti-parallel to one another. Okay. Now in the second figure you can also see actually this first representation in this figure, when you see that the spin of the recoil nucleus is 1 and it is in downward direction, and the spin of neutrino is 1/2 and it is in upward direction. This is actually the tensor interaction. This will take place when there will be tensor interaction. But at the same time, it is you can imagine that it may be possible that a spin of this neutrino is in downward direction, and that of this recoil nucleus is in upward direction. So if the spin of the neutrino is in downward direction and that of the recoil nucleus is in upward direction, then actually it represents the axial vector interaction. Okay, and you know that if there will be actually the tensor interaction, in that condition both of this neutrino and the recoil nucleus must have a spin must have helicity 1. So in this condition, if the process or if the motion or its direction of a spin is just like as tensor interaction, then helicity will be equal to +1. Okay, but if it is axial vector representation interaction, then the helicity will be actually equal to -1. So in fact, in this condition we can simply say that there are two possibilities. In first possibility, you can say the recoil nucleus and neutrino both have helicity +1, and in second possibility we simply say that both have helicity -1. In fact, this +1 helicity of both of the recoil nucleus and the neutrino will be when there will be actually tensor interaction, and their helicities will be -1 when there will be axial vector interaction. Actually, these are two possibilities. I am talking about the possibility, but you will see later on, finally, we will see that actually the tensor interaction is not possible in this case. Actually, the axial vector interaction will be possible, and so finally we will see that the helicity of neutrino will be actually equal to -1. This will be our final result. So before the discussion, you can see or you can remember that after this discussion we will finally conclude that the helicity of the neutrino emitted in this K capture of electron will be -1. Okay, so all these things which I have just explained, everything I have mentioned it here for your convenience. I have written all those things. You can see I am just giving the reading for your clarification. You can see and you can note down these things in your notebook, and that will be just a good notes for your examination purpose. So you can see I have mentioned it here that the entire angular momentum change is carried away by the emitted gamma photon. Okay, the K capture process from 0 minus to 1 minus, so it is pure a GT transition, as the process is 0 minus state to 1 minus state. So you know the selection rule for the GT transition, that it represents a pure GT transition. Okay, and the spin of the emitted neutrino must be anti-parallel to the spin of 961 kilo electron volt SM152 state. All these things I have just explained. I am just giving the reading for your convenience, so because you should then note down these things in your notebook. Now, as I have told you, there are two possibilities. In the first possibility, we simply say that the recoil nucleus and the neutrino both have helicity +1, and this will be +1. Then you say that the interaction is tensor interaction. Or in second possibility, we say that the recoil nucleus and the neutrino both have helicity -1, and this is the case of axial vector interaction. And as I have told you earlier, that finally we will see that the helicity of neutrino will be -1, not +1. Finally, our result will be that. But here I am talking about the possibility, so I have also mentioned that it is possible that the helicity of the recoil nucleus and the neutrino may be +1 if the interaction is tensor. But actually in this process the interaction will be not tensor interaction, but it will be axial vector interaction, and so the helicity will be -1. Okay. Now you can see that the nucleus in excited state must recoil with momentum equal and opposite to that of the neutrino. Why? Because to keep the linear momentum conserved, definitely the direction of momentum of the excited nucleus or recoiling nucleus and the neutrino must be opposite, and magnitude should be same. This is for the validity of the conservation of linear momentum. Now you can see from this equation 1, which I have mentioned earlier, that the total spin or spin angular momentum, you can say, of the reactant, that is the captured electron and this nucleus, parent nucleus EU, this will be what? The total angular momentum will be 1/2 plus 0, that is 1/2. Okay? And the spin or angular momentum of neutrino is -12, and if you consider that the spin of this SM star is I, then to keep the angular momentum conserved, this -1 plus I should be equal to 1/2. So what will be the value of I? I should be equal to 1/2 and plus 1/2, and that will be equal to 1. So you can see that for the validity of conservation of angular momentum, you can say that if the captured electron has angular momentum 1/2 and the ground state EU nucleus has angular momentum 0, then definitely to keep the angular momentum conserved, this excited SM nucleus must have angular momentum equal to 1. So that thing I have actually mentioned it here. You can see that the sum of the initial spins of captured K electron and EU152 nucleus is what? This is 1/2 plus 0, that is 1/2. And spin of the neutrino is -12, and so from the conservation of angular momentum, the spin of excited SM152 will be what? This will be actually equal to 1/2 minus 1/2, that is +1. And so this excited nucleus SM152, you can see here that I have mentioned it, that its angular momentum or the spin is 1, and this minus sign actually represents its parity. Okay. So now see now what conclusion actually we can draw from this result? You can see it means a spin of the excited SM150 nucleus is just anti-parallel to that of the neutrino. And you can see from this figure that I have shown in this figure that the spin of the neutrino is in upward direction, then the spin of the recoil nucleus is in downward direction in tensor interaction. And if you consider that the interaction is axial vector interaction, then the spin of neutrino is in downward direction and that of the recoil nucleus is in upward direction. So it is evident that the direction of spin of the emitted neutrino and that of the recoil nucleus must be opposite to one another. Okay. Now you can see that this excited SM152 nucleus and neutrino both are moving in opposite direction. You can see the figure, both are moving in opposite direction. And as they are moving in opposite direction, so and their spins are also in fact anti-parallel. So in this condition, you can simply say that the helicity of neutrino must be equal to helicity of this SM star 152 nucleus. This must be same. Okay. And so we conclude that the problem of measuring the helicity of neutrino has been reduced to the helicity measurement of the excited SM2 nucleus. It means if you want to measure the helicity of neutrino and you design an experiment to measure the helicity of this SM star 152 nucleus, sorry, the page has been turned, but don't be worried, it will be just okay. And there is some problem in my device, so sometime the page gets turned, but that is not a major problem. It will be just now okay. You can see. Now I was telling you that since the SM star and you are moving in opposite direction, so from this we conclude that the helicity of neutrino and the helicity of SM star 152 must be equal to same. So if you want to measure the helicity of neutrino, what you will do? We can actually measure the helicity of this excited SM nucleus, and that helicity of excited SM nucleus will be just equal to the helicity of neutrino. Okay. So our prime aim is to measure the helicity of neutrino, but for this we can measure the helicity of the excited nucleus, and that will be equal to helicity of the neutrino. Okay. Now you can see that in the transition of ground state, which is actually the 0 plus state, the gamma ray takes the angular momentum with it. It is rather simple to show that by applying the laws of conservation of linear momentum and angular momentum, that the spin of gamma rays must be same as that of the excited SM nucleus, and hence you can say that spin of gamma ray is just opposite to that of neutrino. Okay, opposite to that of neutrino. So you can say that the problem of measuring the neutrino helicity reduces to the measurement of the helicity of the circularly polarized gamma rays emitted opposite to the neutrino momentum. All these things I have mentioned it here. You can see that to keep the angular momentum conserved, it is required that the spin of gamma rays must be same as that of SM152, excited SM152. And thus the spin of the gamma ray is opposite to that of neutrino. Okay. And so as I have told you, if you want to measure the helicity of the neutrino, you can calculate or you can measure the helicity of the gamma ray photon, and that will be actually equal to the helicity of the neutrino. So I have mentioned it here that the problem of measuring the neutrino helicity reduces to the measurement of the helicity of the circularly polarized gamma ray emitted opposite to the neutrino momentum. Actually, this gamma ray are emitted in all directions, but we are interested here only in those which are actually emitted opposite to the neutrino. So you have to see in experiment that the gamma rays which are emitted just opposite to the neutrino, you should measure the helicity of that circularly polarized gamma rays, and that helicity will be just equal to the helicity of neutrino. So finally our problem of determination of helicity of neutrino becomes what? If you want to measure the helicity of neutrino, you should measure the helicity of the circularly polarized gamma ray emitted just opposite to the direction of motion of neutrino, and that will give you the helicity of neutrino. Okay. First of all, I have told you that if you want to measure the helicity of neutrino, you can measure the helicity of the excited SM nucleus, and that will be equal to the helicity of neutrino. But now I am telling you finally that if we want to measure the helicity of neutrino, we can design an experiment to measure the helicity of the circularly polarized gamma rays, and only those gamma rays you should take into account which move actually in opposite direction of the neutrino. In fact, as I have told you that gamma rays will be emitted in almost all directions, but you should focus only on those gamma rays which are moving just in opposite to the direction of neutrino, and measure the helicity of that gamma rays, and that will be just equal to the helicity of neutrino. Okay. Now we will see these things in some analytical way. You can see here. Actually, when an experiment is performed to determine this helicity of neutrino by measuring the helicity of gamma rays moving just opposite to the neutrino, in that condition you can see the direction of polarization of these forward photons was determined by first scattering them from magnetized iron. This is the experimental process, and then allowing them to be resonant absorbed by SM152. The 1961 kilo electron volt quanta have slightly less energy. In fact, as you have seen that the SM152 nucleus, which is daughter nucleus after the electron capture, is actually in the state which is 961 kilo electron volt above its ground state, but actually the this energy state is slightly less than this value 961, and that value is very small, which can be neglected. But what is that energy by which it is diminished is delta E equal to E naught square by mc square, whose value is almost equal to 6.5 electron volt. In fact, here this E naught is the excitation energy of the -1 state because of the recoil loss in the source. Okay, -1 state, this is actually the state corresponding to SM star in the second excited state. Okay. Now, resonance scattering will only take place if the extra energy equal to the energy lost in supplied to the emitted gamma rays. You can see I have shown it here that this is your EU nucleus in its ground state, and from it a neutrino is emitted with energy Ek, and the daughter nucleus is in fact this SM star, and SM star means this is in excited state, and you can see this moves with a velocity v just opposite to this neutrino. Okay, and after that this loses its energy and goes to the ground state, and also via the gamma emission. And so after the losing energy by gamma emission, this nucleus is in its ground state, and then this gamma rays is actually scattered by a magnetized iron scatterer. Okay, so you can see I have mentioned it here, you can see it here, that v is the velocity of the recoiling nucleus after the emission of the neutrino, as you have seen in the figure. And so from the conservation of linear momentum, you can see that the momentum of the excited nucleus, which is mv, must be equal to momentum of the neutrino, which will be ek by c. Neutrino is massless particle, so its momentum is energy divided by c. So the magnitude of the momentum of excited nucleus and the magnitude of the momentum of neutrino must be equal, and direction should be opposite according to the principle of conservation of linear momentum. So you can say that mv is equal to ek by c. This m is actually mass of the daughter nucleus. And so from here you can see that v by c will be ek divided by mc square. Actually this value of v by c will be used in the further calculation, so I have calculated it here. Now if de-excitation occurs before the nucleus slows down, it means the nucleus is moving with same velocity v, but it gets de-excited by emitting the gamma photon. So what will be the energy of the gamma ray emitted in this process? That energy from energy conservation principle, you can give E gamma will be equal to E naught plus V by C into E naught cos theta. And what is this theta? You can see from here, this theta is actually the angle between the direction of the motion of this gamma rays and that of the recoiling nucleus. Okay, and so from energy conservation we have written that the energy of the gamma photon is equal to E naught plus V by C E naught cos theta minus E naught square by 2 mc square. Okay, now you have seen this in this equation 2 that this V by C is ek by mc square. So instead of this V by C you can write ek by mc square. So E gamma is equal to E naught plus ek by mc square E naught cos theta and minus E naught square over 2 mc square. Okay. Now for the resonant condition, or you can say that the excitation energy which can be transferred to the absorbed nucleus SM152 will be what? Excitation energy, that will be E gamma prime, and that is equal to E naught plus ek over mc square E naught cos theta minus E naught mc square. This is actually the excitation energy which is actually transferred to the absorbing nucleus. Okay, you can see actually here the value E naught square by 2 mc square was subtracted, and so when you will actually add in this expression E naught square by mc square, which is actually the excitation energy, you can see it here, then we will get the value of the excitation energy given to the absorbing nucleus SM52. So I have written here that the excitation energy which can be transferred to the absorbing nucleus SM152, This is given by E gamma prime equal to E naught plus Ek by mc square E naught cos theta minus this much. After adding that energy, you get this result. Now, what will be the condition for resonance? In fact, for resonance, this E gamma prime must be equal to E naught. E gamma prime must be equal to E naught. Now you can see when E gamma prime will be equal to E naught, then actually Ek by mc square into E naught cos theta minus E naught square by mc square, what will be this? This will be equal to 0 because E gamma prime is equal to E naught, so this term should be 0. And if this is 0, you can see that this E naught and E naught by mc square is a common factor. E naught by mc square is a common factor, and there will be inside the bracket Ek cos theta minus E naught, and that will be equal to 0. But E naught by mc square is not actually 0. You have seen that this is almost 6.5 electron volt. So definitely this second factor will be 0, and so E cos theta minus E naught equal to 0, or you can say that E cos theta equal to E naught. So these are the conditions for the resonance. Now you can see that the neutrino has the same energy as the gamma ray. In fact, if the energy of neutrino and that of the gamma ray, it means E gamma prime and E naught, if both are actually equal, or here you can see Ek cos theta equal to E naught. If theta will be 0, then Ek will be simply equal to E naught. So from this result we can say that when the neutrino has same energy that of gamma ray, then resonant condition is fulfilled. Resonant condition will be fulfilled only when the energy of the neutrino and that of the gamma ray are equal. Okay. And actually this condition will hold only for those gamma rays which are emitted opposite to the neutrino, and the helicity of the neutrino can be measured by measuring the circular polarization of those gamma rays. Okay, as I have told you earlier, this thing actually. So now there is a famous experiment for the measurement of the helicity of the circularly polarized gamma rays, and this experiment was performed by Goldhaber. So from this Goldhaber experiment, I have not detailed this experiment here, but what was seen in that experiment I have mentioned only here. So it was found from the Goldhaber experiment that gamma rays have left circular polarization, and if the polarization is left circular, then you know that the helicity will be negative. Because we have already discussed these things in the earlier lecture, and you have seen that in case of left circular polarization, helicity is what? That is negative. And in this experiment, it was found that gamma rays have left circular polarization. So from this experiment, we conclude that the neutrino has negative helicity. Okay, as I have told you earlier. Now, if the helicity of neutrino is negative, what actually we get, what information actually we get from it? In fact, the negative helicity of neutrino in K capture shows that in the pure GT transition, Gamow-Taylor transition, the dominant interaction mode is axial vector interaction, not the tensor interaction. So, as I have mentioned earlier, that there are two possibilities, that the helicity of neutrino may be +1 in case of the tensor interaction, and it may be -1 in case of axial vector interaction. But finally, after this experiment of Goldhaber, it was found that the helicity of the neutrino is negative. So you can say that actually interaction in this case is axial vector interaction, not the tensor interaction. So I hope you have understand the concept of the helicity of neutrino. This is actually a very important problem for you. So go through the video seriously, write down these things in your notebook, revise it, and then you will be 100% sure that you can write the answer of the question based on this helicity determination of neutrino in your examination.